Good evening, everyone. Welcome all of you for this week 12 live session for Smart Grid Basic to Advanced Technologies course. Welcome all of you for the Smart Grid Basics to Advanced Technologies NPTEL course. And this is the last live session for this course, week 12. And tomorrow we'll be having one more live session by another TA. My name is Gagan Meena and I'm a fourth year PhD student at Electrical Engineering Department of IIT Bombay in Power Electronics and Power System Engineering specialization. We'll start today's session now. This will be the agenda we'll be following. We'll start with the overview of week 12. Then we will discuss certain questions. And if you have any doubt, you can ask while the session is going on or after we complete with the questions. This is a link for the recordings of live sessions. You already have access to it, and I hope all of you are able to access it. You can go through it. All the this is a link for the YouTube channel, and on the in the problem solving sessions tab on the portal, you can find the link for all the recordings of the live session by all the 3 TAs and also the material used for that particular for each of the sessions. You can find both the material as well as the recordings for the live session on this link. And this is a YouTube link, and you can find the link in the problem solving sessions tab on the portal. There you will find the link for all the materials used. There is a Google Drive link, and you can go through that. All the 3 TAs have uploaded their respective materials as well as the recordings of the live session, their links. And to Wednesday is the last date for submitting the assignment of this week. So please submit it on time. Now we'll start with the overview of week 12. I have been telling you since this week 9 has started, that week 9 onwards we started with the demonstration, week 9 to week 12. So this is the last week, and in previous 3 weeks also we discussed different demonstrations of different concepts which we have learned till week 8. Whatever we are studying, finally we want to apply it in the real time, in the practical world, the real world. And we cannot directly go and have, let's say, for example, we have a new solar plant coming up, or it might be a wind plant also, or any kind of generation. Might be storage also. Now energy storage projects are coming up. If you want to integrate this to the existing grid, we cannot just directly go and connect it to the grid. Because the objective of grid main aim, the primary aim is to provide reliable power supply. And if the interconnection of this particular equipment creates instability or any kind of outage in the grid, then that objective is not met. So we want to provide ensure that this objective is met. And for that, before interconnection, we need to do all kind of studies. We need to follow the standards, follow the grid codes, standards, regulations, whatever are there. We need to follow all these things. That's why we started in week 1. We had gone through different types of standards, like for uh, integration of IBR, integration of distributed energy resources. Standard for that is 1547. And then for integration of IBR at transmission level, there is another new standard, IEEE to 2008. That's a new. This is for distribution system, that is for transmission. For both, we have a different standard. Earlier, we were having a single inch. We had only for DER, for distributed energy resources, and the same was being adopted for transmission interconnection as well. There were many problems because of that, and then IEEE came up with a new regulation, new standard for transmission system separately. So before interconnection, we need to follow all these things. Even after following the is, let's say we have gone through the standards, and still we need to first of all simulate that before real time. Let's say we want to connect 200 megawatt plant. Before interconnecting that to the real world, real power grid, we first simulate it. We have an equivalent of grid, infinite bus, and then, or we can have Thevenin equivalent of the grid at that particular node where we want to interconnect. Once we know this, we can integrate our system. We can simulate it in different softwares. We have PSCAD, RSCAD, OpenRT. In RTDS, which is a real-time digital simulator, all these different types of simulators, this real-time digital simulator or OpenRT, these are hardwares and they have a software associated with them so that we can implement whatever system we want to implement and run it on the hardware. So they provide a software interface also which interacts with the hardware through communication. Ethernet communication is available. And for RTDS, we have RSCAD. And for OpenRT, there is RT Lab. So these are name of software. This is RSCAD. These are softwares associated with these hardwares. In these softwares, what we can do, we are taking, if we consider this example, then in RSCAD, we can simulate our generator, which is 200 MV or maybe. Let's say this is the capacity and we have voltage level also, and we want to connect it to the grid, which is represented by a Thevenin equivalent. And now we want to see how the system behaves. This one we want to see. We want to see the transient analysis. What will happen if there is a fault? Want to do steady state analysis. We need to also test the protection, generation protection scheme. All these things are required beforehand. before actually connecting the system to the grid, we need to do all these different kind of feasibility studies are there. Once we simulate it, we can, and these grid codes and regulation also specify the details of all the different kinds of simulation which are required to be performed, and different all the files need to be submitted to the agencies, to the power grid or whichever agency is meant to undertake these kind of interconnection studies, and interconnection permissions are given by certain organizations. So they require all these simulations files. They will also check it again whether the the output which we are telling them and which we are reporting, whether it's matching with the it's actual or it's fabricated. They will also verify it, and once that is verified, they will grant the uh, interconnection to the grid. They will permit it. So this was for generator, but for, let's say we want to have microgrid interconnection, a small scale microgrid or battery energy storage. Then we can also, after the simulation, we can also test a small prototype of it. We can have a small microgrid, as we have seen in previous weeks also, small microgrid containing a PV, rooftop PV, or a PV emulator or a wind emulator. Then we have storage, small size storage to mimic a real time, a real life microgrid with on a small scale, a prototype. And we can integrate that to the grid, which we can model in the RSCAD. The distribution grid where we want to connect that microgrid, within which that new microgrid will come up, that can be interconnected to that particular grid. And that distribution grid it is modeled within the RSCAD, the real-time digital simulator will act as a grid. And in that grid, we can connect this, our small prototype microgrid, which will be having small actual physical equipments. They are not simulation, they are not just model, they are actual equipment, but on a smaller scale. If we are able to replicate what we have simulated using these small prototypes, then we have this surety that it will be able to mimic it in the real time as well. Otherwise, that's why we go for prototyping, small scale. We have small scale prototype, and we can translate it to large microgrid. Once we are done with this simulation, we can with the high confidence we can say that yes, it will work for the actual microgrid also. Because there are different types of non-linearities also which are there, which we do not see in simulation. It depends on the model, the granularity at which we are modeling the network, or our or the microgrid, which or and the distribution network where we want to connect. The granularity will decide that. If it is very detailed, then we can see most of the things. And they also consider the non-linearities, non-idealities. And that way we can simulate this. So these demonstrations help us to ensure a safe and reliable interconnection to the system by doing this kind of analysis. Okay. This is the objective of all these different kinds of demonstration. Whenever we want to do these things, very detailed studies are carried out using these different types of softwares or different types of these hardware in loop simulations. We would have seen example of this Hyperloop. Hyperloop is a transportation. It's a mode of transportation. There is a cube. There is a tube. A vacuum is created within the tube, and that vehicle that magnetic levitation is used, where it will float in this tube because there is vacuum, and magnetic levitation is used here. So there is no air, friction of air is avoided here because of the presence of vacuum here, and that's why it's able to achieve a high speed. Before actual, let's say we want to create a hyperloop between Mumbai and Delhi, we cannot just directly go and do it. That's why so many companies, they first of all create a small prototype for 1 kilometer, 2 kilometers. IIT Madras has tested a prototype, hyperloop prototype in India. Similarly, in Abu Dhabi also, different prototypes have been, they have been tested for a small, for a shorter distance, so that once they are confident that yes, it's possible, it's there is no problem in within this short distance, then even you see metro trains, when they are, whenever a new line is created, a new line is constructed in metro, then for 1 year they will first of all run several trials every day for a year or so. Once they are confident that everything is running fine, then they will start the actual operation. That's why these kind of simulation, they help us to avoid any kind of mishaps. And grid is a very important aspect. A small outage can result in loss of billions of rupees. It's economic loss. That's why we need to resort to such things. Okay, so in this week we had discussed these different types of demonstration. First was the energy management of a microgrid, then a power hardware in loop for symmetric and asymmetric fault analysis of DFIG. In the last week, we have discussed that there are two types of hardware in loop. One is the control hardware in loop, which is CHIL. Here, control signals up to 10 volts are exchanged between the device under test and the real-time digital simulator. And second one is the power hardware in loop. Here we have exchange of power between the device under test. These devices under test are power hardwares here. While in control hardware in loop, the device are, they work at a smaller voltage levels, 5 volts, 10 volts, not more than that. But these power hardware in loop, they will involve power devices. For example, you have synchronous generator, you can have induction machine, DC motor, you can have a PV, you can have a battery operating at 220 volts. All these things, power devices, they need to be interfaced with the real-time digital simulator. However, the output of this real-time digital simulator, it is only up to maybe between plus minus 5 volts or 0 to 10 volts, while the power device requires a higher voltage level, higher current levels. If you want to integrate this device, this is RTDS, and this is power device. This requires higher voltage levels, and the output here is a smaller voltage. In between, we need something which can amplify the power. That's why we require a power amplifier here, which will amplify the signal, give it to make it suitable for the power device. And power device will give its output. The amplifier will again make it suitable for the RTDS. So this is the low voltage up to 10 volts, less than 10 volts. And this is more than 10 volts. This is for power div. Now 230 volts for single phase. Okay. And current rating is also higher. It is very small current, microampere or milliampere current. But here current will be in ampere. That's why it is called power hardware in loop, because power is exchanged here. And here control signals are exchanged. That's why it is control hardware in loop. Okay, next was a demonstration of ancillary support from a virtual synchronous generator. Virtual synchronous generator, here the example of IIT Roorkee distribution system was given, where it has a peak demand of around 8 or 8.2 megawatts and base minimum demand of around 2.2 megawatts. And there is diesel generator, there is PV of around 2.2 megawatt peak power. Then there is around 600 or 800 megawatt hour of storage is also there. These non-conventional resources are also, they are, their penetration is quite high here in the hierarchy distribution. Therefore, the inertia is reduced here. And for that purpose, to aid this, to replicate this inertia, reduce inertia, virtual synchronous generator is used. Okay, it can provide ancillary services, different kind. It can provide voltage support, frequency support. It will act as a grid supporting device, providing frequency reference. Then demonstration on peak energy management using energy storage. And last one, finally conclusion. Is we'll go through them one by one. This is the first one is demonstration of energy management in DC microgrid. Okay, let us first go through this. Here we can see, so this is a PHI. Here what we are doing, here we are emulating the DC grid, DC microgrid. This is a DC microgrid. DC microgrid is being emulated via using a power amplifier. And this power amplifier is taking input from the polarity. You can see this is polarity here. And polarity is acting like a DC microgrid, emulating a DC microgrid. So within polarity in the RT lab, in RT lab we have designed a DC microgrid having a PV storage and DC loads. And then the output of this polarity is connected to this converter. It's a DC to AC converter. And then this is AC side, this is DC side. We have DC link capacitor here with at 400 volts. And then we have a L filter here to connect with the AC grid. This is the AC grid, which is a grid emulator, emulated using a grid emulator, which acts like a grid. And this is PCC, which is like our MCB, miniature circuit breaker, forms the PCC, and this is the AC load or bulb load in parallel with the PCC. Now from here, because we want to control how much power exchange is there happening between AC to DC. Because if there is, let's say the PV source here is less, PV is not sufficient. The output of PV is not sufficient to meet the DC loads here, and storage is also not enough charge. Then in that case, the power should flow from AC side to the DC side. And for that, we need to have a control system that will ensure that whenever there is some deviation, the power has to flow accordingly. And for that, we need to track this voltage VDC, this DC link voltage. We need to track this current between the two grids, and we also need to take this track track the voltage, this PCC voltage. So UABC, IABC, these are the three sinusoidal three-phase current, the voltage and current signals which are measured using Hall effect based sensors, voltage and current sensors. And these sensors are fed to the controller. And this, because this is a converter and we need to provide the firing pulses to the grid, firing pulses to the gate driver circuits, to the gate driver of these switches in the converter. For each switch, we need to generate the firing pulse, and this will depend upon the control logic which we are using. And this control logic is embedded within this DSP based control. This is a DSP based controller. And this is the control logic which is implemented within this DSP based controller. And this finally, you can see the output of this control logic is this modulation voltage, which is this three-phase modulation voltage, which is provided to the PWM generator of which is there within this DSP. In this DSP based controller itself, there is a PWM generator. If it is not there, we need to generate the pulses also. For that also we need to write a logic. But we already have this PWM generator, EW. So there are PWM pins in the DSP, and we can provide this modulation signal to these pins, and they will generate all the 6 pulses for each of the switches. Okay, so here the important point which is to be noted is these are the three-phase voltages and current, three-phase quantities. This is a VDC is a DC quantity. Right? So we require AC as well as DC quantities as inputs. So this is for AC side and this is for DC side, because we want to control the power exchange between the AC and DC side. For DC side, we have control of the VDC voltage. And on AC side also, we have current and voltages. And these are three-phase quantities. Now, we have discussed in previous weeks also that if the most popular controller which is widely used in industry is the PI controller because of its simple nature, and yet it's also able to provide us zero steady state error because of the integral element. And this is the most simple also and very economical, very cheap and simple PI controller. But for PI controller, the input has to be DC. It takes DC signals. Now these are our inputs, and we need to have controller for each of these. And out of these 7 inputs, 3 for each of the phases of current, 3-phase current, 3-phase voltage 6, and 1 VDC 7. Out of these 7 inputs, 6 are sinusoids. They are not DC quantities, and 1 is DC quantity. For VDC, we can directly use a PI controller. We can see here the DC bus voltage control. Here we have the reference voltage, and this is the actual voltage. The difference is the error, which is given to the PI controller, and which provides the power reference, how much power should flow. It is the reference for the power. And from here we get the current reference. Okay. Now, okay, this is done because this is DC. We can directly use PI controller here. But for the remaining 6 quantities, they are sinusoids. They are not DC. They are sinusoids. So the conventional PI controller will not work here. To enable us, if we want to use the PI, we need to, conventional will not work here. We need to modify it. And the modification makes it a higher order controller. The simplest modification results in a second order controller, which can be seen here. And then it is called as the PR controller, not PI controller. It becomes proportional plus resonant converter. And this is the resonance frequency here. Okay, so this is the PR controller. This here it is a second order converter, but it can be controller. It can be a third order, fourth order. We can make it more complicated, but more complicated, the more it is complicated, the more involved and cumbersome is the design process. Okay, that's why the and okay, let's say for all the 3 quantities, 3 current and 3 voltages, we are using PR controller. That means we need to design six controllers here. If not 6, at least we need to have 3 controllers for the current, which we are using here. For we are tracking the difference, the error of the current, and we are also taking the difference of the voltages. But we are directly using it for, we are using here only for current. Okay. But still, for that also we need 3 PR controller. We need to design 3 PR controllers. Can we do something to save on this? And the thought was this, to say how to reduce number of controllers. So it's already a complex controller. That's why we move to ABC to alpha beta frame. This is the Clark's transformation. From 3 quantity we get 2 sinusoids. These are also sinusoids. Alpha, this ABC, we have 3 phases, A, B, and C. Okay. And this alpha beta is like this. And this space phasor ABC, if we make a space phasor, it will rotate like this at an frequency omega. And alpha beta is a stationary with respect to this straight phasor, which represent this sinusoid. This is a stationary frame of reference. And because it is stationary and the actual sinusoid is rotating, this alpha beta will also be sinusoids. This alpha beta are also sinusoids. But one advantage we get here is that we reduce from 3 sinusoids, we are able to get only 2 sinusoids. We are able to save on 1 controller here. So instead of 3, we require only 2 controllers here. That's why we see here 2 PR controllers are required here. 2 PR. 2 PR controllers and 1 PI for the DC quantity VDC. And this is for I alpha and I beta for current. We convert here ABC current into alpha beta domain. Voltage also we convert into alpha and beta. But our these converters they have three phases. We need to convert alpha beta again into ABC to provide this modulation voltage signal. So again we use the inverse transformation from alpha beta to ABC. Now if we want to use PI controller here, then we can do that also. Instead of PR, we can use PI controller also. But for that, we need to have DC quantities. And for that, we use another transformation, which is DQ, ABC to DQ transformation. And this is called as Parkes transformation. This is not a stationary frame of reference. It is a rotating frame of reference. Here, alpha beta are stationary. This frame of reference is stationary. But this DQ frame of reference, it is at an angle with this phasor. Some angle theta, let's say. This is at some angle theta, and this is also rotating, and this is also rotating. Let's say the resultant is this. This. This is FDQ. And this is our actual phasor. And this is also rotating at omega. Both are rotating at same frequency, same speed. And because of that, it appears that this DQ frame is stationary with respect to the ABC. That's why we get these DQ quantities as DC quantities. So this is also rotating. In steady state, it will be a DC quantity. There will not be, it will never be sinusoid, but in transient, there might be some oscillations. In steady state, they are DC signals. In transients also, we can track them. The PI controller can do something to track the transition, but these are not sinusoids. So we can use, instead of PR, we can have PI here, but then we need to change this. Instead of alpha beta, we need to use the DQ frame Parkes transformation. Okay. This was an important point. So one is called, so we have two, Clark's and Parkes. So this is stationary frame of reference. Because it is stationary, the resulting quantities are also sinusoids. Alpha beta, these are also sinusoids. On the other hand, we have Park. This is rotating frame of reference. Rotating at the same speed as the actual phasor, ABC quantities. Rotating frame of reference. And this provides us the DQ quantities. And these are DC signals here. Okay. And that's why we are able to, that's why we use here PR controller. And here we can use PI controller also. So this is a summary kind of thing which you can remember for your exam also. This you can come across this such questions about Park and Clark's. Which one is Park? Which one is Clark? Which one works with DC quantities? Which works with sinusoids? And this is an important concept which you can always remember. Okay. Yeah. So this now that was the energy management in the microgrid. Next was the PHIL, power hardware in loop implementation, experimentation for the symmetric and asymmetric fault analysis of a doubly fed induction generator. Okay, so this is a power hardware in loop. We have already discussed that in power hardware in loop, there is exchange of power between the device under test and the RTDS, the real-time digital simulator. And that power transfer is made possible because of the power amplifier, which amplifies the signal by taking input from the RTDS, which is a low voltage signal. It amplifies it and give it to the device under test. And here the device under test is DFIG, the double fed induction generator, which is this one, which is made using the combination of a DC motor and this induction generator. Here this AC motor used to emulate to emulate different types of wind characteristics. Okay, so here in RSCAD is the simulation of the system where to which this DFIG will be interconnected. Okay, that system is that network is modeled here in the RSCAD, and from here we take the output and we do proper scaling is required here so that the output falls within 0 to 5 volts or plus minus 5 volts. Okay, so voltage, we are taking voltage signal out, then voltage will always be positive. It will be between 0 to 5 volts. The scaling needs to be done properly so that again when we give input here, again it gives us the same magnitude. If scaling is not done properly, then that magnitude will be different. Similarly, that magnitude here will be different if scaling is not done properly. So the 230 volt within this RSCAD should give 230 volts here also. If scaling is not done properly, then this might be something else, which we don't want. The scaling is very important. Once the scaling is done, we take output from the RTDS because this software, the model which is run in this software is simulated on this hardware. So from this hardware, in each of these racks, behind these racks, we have such cards, different types of cards. This is a 12 channel card. We can take 12 output from this, 12 signals we can take out as output from this card, single card. So this is gigabit transfer analog, gigabit transceiver analog output card. This will provide us analog output between 0 to plus minus 5 volts, but here we have voltage. It will be between 0 and 5 volts. We get everything here is in digital domain in the RTDS, within RTDS. And we are taking here analog output. So it will convert, there is a DAC here, which will convert the digital into analog signal. And once we have analog signal, this is a low voltage signal. It's up to 5 volts. That's why we use a power amplifier here, which will amplify the signal and we get a suitable voltage which is suitable for this DFIG operation. And here, from here, we take the voltage and current signal sensors. Using the sensors, we measure these voltage and current and we give it as inputs. These are also analog input. All these are analog signals. That's why we give input to the analog, the gigabit transceiver analog input card. And then after filtering, it goes to the RSCAD. Within the RSCAD, in RSCAD, we have these, for each of these card, we have one software module within this RSCAD. We can map. Let's say these are 12 channels, right? We can provide 12 inputs. We can specify in RSCAD that on which of these channel we are giving the input. We need to specify that so that it will retrieve information or signal from that particular channel only. The other channel might have some noise and that will create trouble. You need to specify which channel is being used, and that can be done within this RSCAD platform. Okay, is this clear? Shall we move ahead? Okay, yeah, same thing is shown here, how the input and output are given. This is for the gigabit, right? So gigabit transceiver analog input card. Okay, now just to show how it works, a simple case is taken here. A function generator is used to provide input to the analog card. In the here, what we were doing here, we were giving input through the actual DFIG. But here, input of voltage and current sensor signal from power device. Instead of function generator, we are using here this voltage and current signal from DFIG. But for testing, function generator is being used here to give a small voltage. Okay, and it's given as input. And thing with this is the thing which I was talking about. Within this is available in the RSCAD in runtime. So in RSCAD you will find there are two files. One is a simulation file where the model is simulated. And another is a runtime file. Once we have simulated the model, we have another file where we can see all the output. We want to plot something, we want to display the values, we want to see all the different types of whatever quantity we want to see in the output. We can see the output in different forms and graph and bar chart, plot, displays. Using switch, we can make things on and off control. All these things is possible. There are push buttons in runtime file. All these things are available. So in the model, we need to specify this model file. One of the component is this card, GTAI X from GTAI. In this, we need to specify which of these channel is being used for input. Then it will go through filter and finally go to the model, which will do the real-time simulation. Similarly, same thing applies for the output also. Here the reverse process happens. Here the simulation is happening in RSCAD. Model is built here. It will run on RTDS. Then after proper scaling, output is taken from one of the channels of this, and this GTAO card, gigabit transceiver analog output card. Then we need to specify which channel is being used to take the output, got the output. And then we take the output on CR. And we can visualize it. In our example, instead of CRO, we have a power amplifier here, which will amplify the signal and give it to DFIG. And this is for just plotting the signal. We can use some CRO or DSO digital. Okay. And say this is the demonstration of this ancillary support from the virtual synchronous generator. This is also a power hardware in loop, and Here also we have this power amplifier here. Whatever discussed here is shown here. You see, this is the RTDS, real-time digital simulator. Which runs the model built in RSCAD. We have model in the RSCAD simulated, which simulates the power system which we want to simulate. Let's say here it was the IITR distribution system which was simulated, and on the particular bus where we want to connect, or where we want to connect this voltage, this virtual synchronous generator, there we can take the voltage and current voltage measurement. We take it out because it's a digital signal. So GTO will convert this digital into analog, and from there it will make it available as plus within plus minus 5 volts. So this signal here is between plus and minus 5 volts. And then we use the power amplifier here. This is that it's called this stage is power interface, because this is a stage where there is an exchange of power between the RTDS and the virtual synchronous generator. The power amplifier requires an external power source, and we have an amplifier here, and at the end it will give output to the VSG, which is a high voltage, which is in order of 200 volts kilovolts. And from here we can take measurement, which will convert the analog into digital. Once we sense the voltage and current, which are analog signals here, the output of our amplifier are analog. Can provide digital also. We are taking here analog because we need to operate a physical device which take analog inputs. We sense the voltage and current. So here current measurement is being taken. Then because it's analog, we need to convert into digital, and this happens within the power amplifier itself. It will scale the signal, and then again it will provide finally a digital output, and this will go to the RTDS. It will go as input to the RTDS, where it will again.
Hello.
Yes, anyone saying something? Is there any doubt?
सर हिंदी में बता सकते हैं क्या?
ओके, हाँ बता सकते हैं। अभी तो आप पहले बोल देते तो मैं पहले से बता देता। आपको अभी तक कोई समझ, फिर आप पूछ सकते हैं, आपको जो समझ नहीं आया मैं वापस रिपीट कर देता हूँ।
सर कुछ भी समझ नहीं आया, हिंदी में बता सकते हैं?
ठीक है, आप पहले बताते तो अच्छा रहता है। आपने इतनी देर से आप सुन रहे हैं। सॉरी। ठीक है, मैं ये बोल रहा था कि ये लास्ट के 9 वीक से लेके 12 वीक्स का जो डिस्कस किया था हमने इस कोर्स में, वहाँ पे हम पूरा डेमोन्स्ट्रेशन देख रहे हैं। जो भी हमने पढ़ा वीक 8 तक, अलग अलग कॉन्सेप्ट्स हमने पढ़े थे, तो उसको कैसे प्रैक्टिकल लाइफ में, रियल वर्ल्ड एग्जांपल में कैसे उसको इम्प्लीमेंट कर सकते हैं। अगर रियल लाइफ में हमें कोई भी, जैसे किसी माइक्रोग्रिड को हमें किसी डिस्ट्रीब्यूशन सिस्टम में कनेक्ट करना है, अगर तो हम डायरेक्टली तो कनेक्ट नहीं कर सकते हैं, उसके लिए हमें पहले बहुत सारे टेस्ट करने होते हैं, क्योंकि अगर हम डायरेक्टली कनेक्ट कर देंगे और कुछ गड़बड़ हो गई तो कंज्यूमर्स को प्रॉब्लम होगी, और वो हम नहीं चाहते। हम हमेशा चाहते हैं कि कंज्यूमर्स को इलेक्ट्रिसिटी हमेशा मिलती रहे, रिलायबल पावर सप्लाई रहे, हमेशा 24/7 पावर रहे, इलेक्ट्रिसिटी सप्लाई कंटिन्यू रहना चाहिए, ये ऑब्जेक्टिव रहता है। पर तो इसलिए हम डायरेक्टली कभी कनेक्ट नहीं करते, और उसके लिए हम बहुत सारे सिमुलेशन करते हैं। हम उसके लिए हमारे पास बहुत सारे सॉफ्टवेयर्स हैं, जैसे PS कैड एक सॉफ्टवेयर है, सिमुलिंक भी यूज करते हैं, मैटलब का है। फिर RS कैड है, RTDS एक हार्डवेयर है, तो यहाँ पे देख रहे हैं ना हम, ये जो है ये एक हार्डवेयर है, ये एक हार्डवेयर है, और इसका एक सॉफ्टवेयर भी होता है इसके साथ, उसको हम बोलते हैं RS कैड। ये RS कैड उसका सॉफ्टवेयर है। तो जैसे अगर हम कोई माइक्रोग्रिड है, हमारा एक छोटा माइक्रोग्रिड है, उसके अंदर सोलर PV पैनल है एक, और उसमें एक स्टोरेज है, मान लेते हैं लिथियम आयन बैटरी है, एक बैटरी है, और कुछ DC लोड है, कुछ DC लोड्स हैं, ये सब एक माइक्रोग्रिड बना रहे हैं ये सब मिलके। और इस माइक्रोग्रिड को हम कनेक्ट करना चाहते हैं हमारे डिस्ट्रीब्यूशन सिस्टम से। तो क्या कर रहे हैं हम यहाँ पे, एक्चुअल माइक्रोग्रिड तो बहुत बड़ा होगा, हो सकता है उसमें पावर प्लांट है, जो सोलर पावर प्लांट है वो 1 मेगावाट का हो, और स्टोरेज भी है वो 1 मेगावाट का हो, या 500 किलोवाट का हो, DC लोड भी ज्यादा होगा। पर इतना हम लेबोरेटरी में इतना बड़ा सिस्टम लगा नहीं सकते हम टेस्ट करने के लिए, तो उसका एक छोटा वर्जन लेके आते हैं हम। तो सोलर पावर एक छोटा पैनल हमने, या PV इम्यूलेटर बोलते हैं उसको, जो एक बड़े पावर प्लांट की तरह काम करेगा। तो 2 किलोवाट का मान लेते हैं हमने, एक छोटा सोलर PV प्लांट को इमुलेट कर रहे हैं, मतलब एक डिवाइस होगा जो सोलर प्लांट की तरह बिहेव करेगा, उसी तरह काम करेगा, वैसा ही आउटपुट देगा जैसा एक एक्चुअल सोलर PV प्लांट देता है। तो वैसा डिवाइस लैब में होता है हमारे पास। उसी तरह हमारे पास एक छोटी बैटरी भी है, पर ये एक्चुअल फिजिकल डिवाइस है, जो कि एक बड़े डिवाइस की तरह, एक्चुअल 1 मेगावाट वाले सोलर प्लांट की तरह ही काम करेगा, बस इसका साइज छोटा है, क्योंकि ये हम लैब में रख सकते हैं। और ऐसे लिथियम आयन बैटरी है, वो भी छोटा है, और DC लोड से हमारे पास। तो ये सब छोटे छोटे डिवाइसेस हैं, और इन छोटे डिवाइस, क्योंकि ये भी उनकी तरह ही काम करेगा जैसे रियल लाइफ में है, तो इनको हम कनेक्ट कर सकते हैं डिस्ट्रीब्यूशन सिस्टम में। अब इनको जाके भी हम सीधे डिस्ट्रीब्यूशन सिस्टम में कनेक्ट नहीं करते, इस डिस्ट्रीब्यूशन सिस्टम को पहले हम मॉडल करते हैं। जो एक्चुअल पूरा डिस्ट्रीब्यूशन सिस्टम है उसको हम बनाएंगे, एक सॉफ्टवेयर के अंदर मॉडल करेंगे। इस सॉफ्टवेयर में बहुत सारे कंपोनेंट होते हैं। आपने यूज किया कभी सिमुलिंक या कोई सॉफ्टवेयर?
नहीं सर।
वैसे हमारे पास सॉफ्टवेयर होते हैं, उसके अंदर आपको रजिस्टर मिल जाएगा। जैसे मान लेते हैं एक छोटा सा सर्किट हमें बनाना है, ये एक वोल्टेज है, DC वोल्टेज सोर्स है, एक रजिस्टर है, और मान लेते हैं, ठीक है, एक और रजिस्टर है यहाँ पे। ये एक छोटा सा सर्किट है, 5 वोल्ट की बैटरी है, और 2 रजिस्टर है। तो ये जो सॉफ्टवेयर्स होते हैं, इनके अंदर आपको बैटरी मिल जाएगी, आप बैटरी को उठा के यहाँ पे लगा सकते हो, और वायर मिल जाएंगे, ये वायर्स है, और रेजिस्टेंस ऐसे ही सब मिल जाएगा, PV पैनल मिलेगा, बैटरी मिलेगा, जो भी हमें चाहिए सिमुलेट करने के लिए सब मिल जाता है इसके अंदर। उसको हम कनेक्ट कर देते हैं, और फिर रन बटन होता है उसमें, एक रन प्रेस करेंगे वो चल जाएगा, आउटपुट देगा वोल्टेज करंट। तो वैसे ही हम क्या करते हैं, इस पूरे डिस्ट्रीब्यूशन सिस्टम को हम इसके अंदर मॉडल कर सकते हैं। जैसा डिस्ट्रीब्यूशन सिस्टम असली में काम करता है वैसा ये भी आउटपुट देगा। तो इसको हम डिस्ट्रीब्यूशन सिस्टम में मॉडल कर देते हैं। हाँ, तो RS कैड मॉडल कर दिया, ठीक है। अभी ये तो इसमें मॉडल कर दिया हमने, पर मुझ हाँ, कुछ डाउट है आपको?
सर एग्जाम में कौन कौन क्वेश्चन आएगा?
एग्जाम में क्वेश्चन कैसे आएंगे, जो आपने आपने असाइनमेंट्स किए हैं ना?
जी जी।
तो असाइनमेंट्स में जिस तरह के क्वेश्चन है उनसे सिमिलर क्वेश्चन से पूछे जाते हैं। तो अगर आप असाइनमेंट्स अच्छे से करते हैं और जो भी टीएस बता रहे हैं, ये जो जो मटेरियल यूज हो रहा है, अगर इनको भी आप देख लेंगे और असाइनमेंट्स कर लेंगे तो आप कर पाएंगे, काफी क्वेश्चंस कर लेंगे आप। इसलिए जो भी
थैंक यू।
मटेरियल यूज करते हैं लाइव सेशन में, वो पूरा एक समरी जैसा है सारे वीक्स के लिए। हर एक वीक का एक समरी जैसा है। तो अगर आप उसको यूज करते हैं तो आपको बहुत फायदा हो जाएगा उससे।
थैंक यू
आपको
सर।
सारे लेक्चर्स वापस से सुनने की जरूरत नहीं पड़ेगी, आप उनको डायरेक्ट यूज कर सकते हैं। ठीक है।
ठीक है सर।
तो ये एक्चुअल सोलर प्लांट, लिथियम बैटरी, इनको कनेक्ट करना है हमें, जो डिस्ट्रीब्यूशन सिस्टम हमने सॉफ्टवेयर में बनाया है। और ये जो सॉफ्टवेयर होता है, इसका जो आउटपुट है वो सिर्फ 5 वोल्ट्स होगा। पर ये सोलर पैनल तो 220 वोल्ट पे काम कर रहा है। अब ये दोनों को कैसे कनेक्ट करेंगे आपस में, कैसे वो एक दूसरे से पावर एक्सचेंज करेंगे, उसके लिए क्या करते हैं, पावर एम्पलीफायर यूज करते हैं। ये 5 वोल्ट को बनाएगा 220 वोल्ट, और इधर फिर ये दोनों एक ही वोल्टेज लेवल पे आ जाएंगे, आपस में वो पावर एक्सचेंज कर सकते हैं। तो ये एक लूप बन गया फिर। ठीक है, ये लूप बन गया एक। और इसके अंदर, इसलिए इसको बोलते हैं पावर हार्डवेयर इन लूप। पावर, क्योंकि पावर का एक्सचेंज हो रहा है और हार्डवेयर है यहाँ पे। ओके, लेट अस मूव टू, this is demonstration of ancillary support from virtual synchronous generator. We were discussing this. So this is the power interface, which is the power amplifier is providing us with this power interface, where the input here is a small voltage, low voltage signal, 5 volts, and the output of this power amplifier is a higher voltage level, up to between plus minus between plus minus 200 volts, and which is input to this virtual synchronous generator. Same thing is shown here. This is the actual hardware system. The IITR distribution network is modeled within this RTDS. So we have 6 racks here, and each rack can simulate 72 nodes. That means 24 bus system. 24 bus. Each bus is a 3-phase. So 24 bus 3-phase system. Here each node represents a single phase. That's why one bus means there are 3 phases ABC. So we have 24 3-phase buses, and we can simulate 24 into total 6. 144 bus system can simulate in on 6 racks. On one rack we can have a 24 bus system. That's why in this we can have this 144 bus network within the RTDS, 6 racks. So that distribution network is within this RTDS, and from its output card we can take input. Means we take output from its card and we can feed it to the power amplifier. From power amplifier it will go to the virtual synchronous generator, which is this. This is acting as the virtual synchronous generator, and this is controlled using this controller, FPGA based controller. And this is the software associated with this FPGA based controller. Here we can visualize the all the parameters of this virtual synchronous generator. Similarly, the network is within the RTDS, but its implementation, the network is simulated in this RS CAD. Here we model this network, and via Ethernet cable it runs on this RTDS hardware. So we have powerful processors in RTDS which are able to simulate this network at a very high frequency. Is this clear? Do you have any doubt? Just drink some water. Okay. I hope it's clear that why power amplifier is used in PHIL loop, power hardwaring loops. But in CHIL we don't require them. And here two case studies were considered. One was disconnection of solar PV. If solar PV is disconnected, then what will happen? The load is more and generation is less. There will be a drop in frequency. In that case, the virtual synchronous generator has to pick and it has to provide more power and bring the frequency back to its nominal value. And then a connection of induction motor load. Here also the load is increasing. Again, the frequency will fall. And the virtual synchronous generator will have to come into the picture. Okay, the last one was this. The demonstration of peak energy management using the energy storage system. This is the reason why do we need energy storage, especially in India and most of the places. Although wind and solar are the two major renewable energy resources, however, the quality of wind resource is not that good in India, and mostly that is restricted to the coastal areas. In other areas, we are dependent more on solar, in solar power. In distribution network, most of the states you will find solar power, rooftop solar plant, and this is a typical profile, a load profile over a day. And if we see in daytime when the solar is at peak and solar is available, this is over and above the load. This is the surplus power which we have. The load is this is light load condition in daytime. Load is less, but generation is more. So if we are not storing this, then this will be simply wasted. We'll have to curtail the generation. We need to curtail the solar output. And on the other hand, if we see in early morning and in the evening, there is a peak. We have two peaks, morning peak and evening peak. Here the load is more, but there is no PV generation. If we can store this surplus during daytime, and then we can utilize it here to meet the peak demand, both peaks, the morning and evening peaks. Then we can make this load profile flat. close to flat. If not flat, then yes, at least we can minimize the difference between the peak and the maximum and minimum load. This we can minimize, and this increase the efficiency of the generator, especially the thermal generators, because if we see, they need to, here they are operating only, they will be operating only for a short duration. For the rest of the day, they are not operating. Their efficiency, that it is not economical for them. It's always good if they are operating near to their capacity. And that is possible when the load profile is near to flat. And here, having energy storage can help us store this excess PV generation during the daytime, and which can be used to meet the morning and evening peaks. That's very helpful. It is beneficial for thermal generators also, and for it is also preventing any kind of spillage of renewable. We are able to store it, avoid any kind of wastage, curtailment. Second thing here, you can see an active distribution system. Earlier till now, we were having distribution system or passive, in the sense that this is a substation, and from substation we have different feeders, and in these feeders we have different laterals. Okay. Okay. Initially, there was no power source on this load side. These are all different loads, and power used to flow in only one direction. Unidirectional power flow is there. Because there is no other source of power flow. Power used to flow only from substation towards the load. But now in this active distribution system, we have distributed energy resources. Different, we have PV plants, let's say, here. In the daytime, when the PV is at its peak and the load is also less, then the local supply is more than the demand. Let's say particular bus, the load is, let's say, 100 kilowatt and generation is 300 kilowatts. Let's say 150 kilowatts. So 50 kilowatt is more generation here and the load. Then this excess generation will 100 will go here, 50 will go here. Earlier, however, if the load is 100 kilowatt and due to cloud cover, this is only 80 kilowatt. Then the remaining 20 kilowatt will come from the grid, from the substation. So this is manageable. This is as per what we have been working till now. The unidirectional power flow, the passive distribution system. But now here, because of excess PV generation, which is more than the load requirement, power is flowing back to the substation. This is reverse power flow. And because of this, there are many problems. We have already seen in the previous weeks that there are problems. The bidirectional power flow creates problem for the protection system. It creates changes in the fault current, and for that we need to have adaptive protection. We have seen And we also saw that the traditional distribution systems, the overcurrent relay was sufficient because of unidirectional power flow, but because of bidirectional power flow in the active distribution system, directional element also is also required. Directional overcurrent plus directional element both are required for fault identification and classification. Hmm. So if we have storage, we can store this excess energy and utilize it during the nighttime. The peak energy management, yeah, this results in voltage regulation issues in active distribution network. What happens here, because here the power is more, generation is more than the load, here the voltage rises, voltage increases here, and power flows here from high voltage to low voltage side. There is a more voltage here. And in passive distribution system, the problem was of voltage regulation because the voltage used to be lower on the lower side on the far end of the feeder. Especially in the long feeders in rural areas, you would find it's quite long, more than 1 to 2 kilometer long feeders. The voltage at the far end of the feeder would be less because of the drop along the feeder. But here we are seeing a reverse situation. Here the voltage used to be, let's say, 0.93 per unit, and this is 1.0 per unit, and it is less than 0.95 per unit. But here this is supposed to be 1 per unit. Here voltage is more than 1 per unit. So this is reverse phenomenon. Earlier it used to be less than 1 per unit, now it is more than 1 per unit. And because of this, there is a reverse power flow. And same way, this happens when there is a low PV and high PV output is less and the load is also less. But if PV output is less and load is more, then there will be voltage drop. Then there will be voltage uh, drop issue, low voltage condition. Okay, yes. So here we have voltage regulation issues in active distribution network. Over voltages when in summer afternoon, when the load is less and the PV generation is quite high. Under voltages when generation is low and load is more. And this happens when there is cloud cover, the output of PV reduces. Heavy loading condition, load is quite high, more than the generation, then also there will be under voltages. Cloud transient and heavy loading. Then how energy storage can help? Mm, These are the different advantages or applications of energy storage. Let's say here there was under voltage, right, or over voltage. In both the situation, energy storage can help. In over voltage, because there is excess generation than the load, energy storage can charge in that case. Under voltage, energy storage can discharge. And here it can charge. It will be able to control the voltage. Then PV output smoothing. The PV output is it's very, first of all, it is intermittent. And then it is uncertain also, stochastic, very fluctuating. Storage can help smooth out the uh, output from a PV plant. Then peak load shaving, we have seen here. If the PV surplus PV is stored here, then this peak will be reduced because this battery will discharge here and it will reduce the load requirement, net load requirement. Minimizing power losses, how power losses will be minimized? Because the power losses happen when we saw this from substation, the power is going to traveling a long distance. There are voltage drop here. So I square losses are there. Instead of this, let's say here load was 1 kilowatt and we were having a PV and storage here, battery and PV plant. And these two together are able to meet this 1 kilowatt requirement. Then the power need not travel from substation. There is no requirement. The requirement is being met locally. Then there will be no losses. Losses will be reduced here. Because the requirement is being met locally, the power losses are minimized. And this will also minimize the line loading. Because requirement is being met locally, then uh, the requirement of wheeling the power through the lines will be also less. This is the real-time voltage variation in PV integration. And here you see we already discussed this, that over voltage, when there is excess generation in the load, it signifies that there is high PV penetration with lightly loaded condition. So the generation is quite high. The generation is more than the load, and because of that, there is over voltage. Then we also see one under voltage is there when there is absence of PV and there is high loading condition. Then it will lead to low voltage at some of the locations. That's why for effective utilization of surplus PV, deployment of energy storage can be very helpful. And this is the PHIL implementation for the peak energy management. So here we can see this is the ITR distribution network. Here it is considered that there are five energy storage which are already present in the distribution network. And before integrating these energy storage into the network, we need to know where and how much. So location. And how much means capacity. So these two things are required. And also, as you can see, how many units are also required. How many units of what capacity and at what location. This we need to determine first. because we want to know the location. Let's say we have 24 buses. It's a 24 bus system, and so we have possibility that at each of the buses we can have a storage or not. Right? So 24 buses, each of this, there is a possibility either there can be a storage or there cannot be. One, if storage can be there. If storage is, it can be present, or zero means storage is not there. One means storage is, there can be storage on that particular bus, and zero means there is no uh, storage on that bus. It's a binary variable. This is a decision variable. We don't know a priori on which bus we want to have. We want to know at which bus I should integrate the energy storage in order to achieve certain objective. The objective might be loss minimization, minimize losses, minimize losses, or minimize the voltage deviation, or it can be a combination of both. Okay, and that's why it becomes an integer programming and makes integer linear. Although the distribution system is non-linear. If you write the equation of voltage and current, then in terms of power and reactive power, or PQ in terms of voltage and current, then it will be a non-linear equation. These are non-linear equations. We can consider a linearized power flow here. We can linearize them using, there are different methods. We can linearize them, and then we can use this linearized power flow model, and then specify these integer variables and write constraints for energy storage. We have, for energy storage, the unknown will be location is the unknown first, and for that we have 24 binary variables, one for each bus. Then we don't know power rating also, but yes, we have some limit that it should be less than some specified maximum P at each bus. So we have these 24 power variables, and we also want to calculate energy limit. There is a limit. There might be some minimum limit also, but we want to find out this E also. This is also a variable. So 24 energy variables also, and we have these limits, and both it's greater than zero. And then we have energy update equations for each bus for different time blocks. So T plus 1 is equals to T plus if it charges. Minus discharge. Okay, into delta T. So this is the energy update equation. So these will be the constraint for energy storage. And then after solving the problem using different solvers, there are different solvers, different packages where we can write these optimization problem and we can solve them using different solvers. Once we solve them, then we find out, we will get these location, how many, at what all buses we should have this energy storage, and what should be the rating, the energy and power capacity. All these three things we can output of the optimization problem will be these three quantities and where. The power capacity, energy capacity, and location. Or you can say bus number. These will be the output. Once we know this, we can have the energy storage at those particular buses. And this model finally is simulated within the RSCAD and run output, and it is simulated on this RTDS. Now we want to check how this integration of this energy storage at a particular bus will help. How will it improve the voltage in the distribution system? Is it actually helping? Is it able to keep the voltages within that band of the voltage? That means between 0.95 to 1.05 per unit. That we need to see, check. And for that, once we know, once we have the model ready, and we want to, we also have decided at which bus we want to monitor the voltage. Then at that particular bus, we can provide the signal from the from this battery via the power amplifier. So here we have a battery emulator, which is at its output will be a 200 volt. The same grid emulator here. This is a grid emulator which we have used in previous weeks for all different types of for interconnecting microgrid or any whatever. So this was being used as a grid emulator as a source of as a AC source. But here it can also be used as a DC source. Here for battery emulator it is acting as a DC source, and its rating is 40 ampere hour 200 volts, and this is a three-phase bidirectional converter because we want to check both higher. We want to solve the problem of both under voltage and over voltage. So in over voltage, if at a particular bus there is over voltage, that means generation is more than the load. That means the excess generation needs to be stored. Power flow will be like this in case of over voltage. The battery will charge. And in case of under voltage, that means load is more, the battery should discharge. So it will reduce the net load and increase the generation. So in case of under voltage, it will discharge. That's why we need a bidirectional, a three-phase bidirectional converter here. And this is being controlled using this wavelet based controller, which is generating the PWM signals for the bidirectional converter. And using the L filter, we are connecting it to the power amplifier. Here we have this ABC voltage and current signals, which are being sensed and fed to this controller, wavelet controller, which will be generating the PWM signal. And the output after the L filter goes to the power amplifier, which will make the signals suitable for integration into the or input into the RTDS. It will reduce the voltage level. Here it was 200 volts. Now it will make it within plus minus 5 volts and give it to the distribution network, which is in the RTDS. So input from power amplifier to the GT AI card will be within plus minus 5 volts, but internally it will be same as 230 volts for the distribution network. Depending upon what the scaling factor is, it will convert. It will reflect it as a 230 volts. And that way, both under voltage and over voltage scenario can be tackled here. Okay, is there any doubt? So for energy storage siting, binary variables are introduced. That's why it becomes a MILP if we are using a linearized power flow. If we are using the actual nonlinear power flow, then it will become an mixed integer nonlinear programming, MINLP. The final was the information about different types of smart grid pilot projects. This was the last part of this week. Uh, So these were the goals of different smart grid pilot projects. Advanced metering infrastructure, which we discussed in the first week itself. Then power quality management. This also we have discussed. We have gone through different kind of power quality issues, spikes. So there are two types of power quality issues which we have seen: current based and voltage based. In voltage based, we had seen voltage sags well, right, and voltage unbalance. In current, we have seen flicker, harmonic, notches, and all these things. Then outage management system. Whenever there is a fault, the system should be able to, first of all, identify the fault, then localize it, identify the location, and then disconnect the faulty section and quickly restore the power to the healthy section of the system. And then again, uh, mitigate, remove the fault, and again connect the unhealthy section back to the healthy section. Resume power to the unhealthy section once the fault is cleared. This should happen automatically. That is the self-healing part of the smart grid, which we have seen in the first week. The objective of a smart grid. It has one property which is self-healing, and another property was resilience. How fast, how quickly it's able to come up, restore the power. First of all, mitigate, and then how fast the system is able to quickly uh, resume the supply to the unhealthy section. And peak load management, we have been discussing this point again and again, that we want to have a flat load profile, and for that we also discuss that demand side management, demand response, different strategies like peak shaving, valley filling, then real-time pricing, peak pricing, and that's, all these things we had discussed. That was in the peak load management, and then we had also gone through different types of distributed generation, conventional as well as unconventional based. In non-conventional, we have solar, we have PV, micro turbines. Now, one company is also coming up with the residential compressed air energy storage, small compressed air energy storage for a residence. Right now, they are in pilot phase, but by 2027, they are claiming that they will be providing actual product, fully operational product by 2027. See, so now we can have small, even wind turbines over home for each residence, just as we have a solar, the rooftop solar PV. We can have rooftop the small wind turbines. We can have micro turbines in home and residences. All these things are coming up. Then energy electric vehicle is also there, which can support vehicle to grid and grid to vehicle, both type of operations. So these were the goal of smart grid pilot project, right? Okay, now let us go through the questions for this week. The first question is, which of the following statements is are correct for active distribution network? The first one is, over voltage signifies high PV penetration with lightly loaded condition. Okay, I'm sharing the screen again. Yeah, I hope it's visible. Yeah, it's visible. It's visible. Which of the following statements are correct for active distribution network? The first one is, over voltage signifies high PV penetration with lightly loaded condition. Second, absence of PV and low loading conditions lead to low voltage at some location. And deployment of BSS can be helpful for effective utilization of available surplus PV generation. So here we have to see, over voltage signifies high PV penetration with lightly loaded condition. Yes, it is correct, because here generation is much more than the load. Its generation is more than the load here. That's why it results in over voltage. And if PV is not there and load is also less, absence of PV, and if this is not low loading and there is absence of PV, that means load is more than generation, then in that case there will be low voltage. But here PV is also not there and load is also less than, we uh, cannot say anything about the voltage here, because we don't know how much is what's the relation between the generation and load. Third is deployment of BSS. Yes, we already discussed this figure, right? This one. that surplus we can use to meet the load. So BESS can be helpful for effective utilization of available surplus PV generation. That is true. Now, so option A and C are correct here. Second question is, which of the following optimization model was used for optimal storage siting? This also we have discussed that actual distribution system model is non-linear, but we use a linearized power flow. This becomes a linear model, and because we are citing energy storage, we don't know at which bus the storage should come up. So for each bus, there is a binary variable associated with that bus. Either it's 1 or 0. If it is 1, that means energy storage will, that's an optimal site for one of the optimal sites for energy storage. And if it is 0, that means energy storage should not be sited at the particular bus. If we combine these two options, linearized power flow and then binary variables for the energy storage siting, then it becomes a mixed integer linear programming. Actually, it is a mixed integer nonlinear programming. It can be quadratic if the objective function includes quadratic cost curves. Then it can become MIQP also. But we used MILP. It is QP. It cannot be QP because integer variable has to be there for citing. Similarly, SDP is also cannot be there. Integer variable has to be there. SDP is semi-definite programming. Okay. Next question. This is the third question. What is or are the probable causes of errors during PHI? First is transformer for connection of this is two subsystem. These two substation. These transformers are these inter-rack transformers. These are the inter-rack transformers. The two subsystems are connected by using these two using this inter-rack transformer, and then is and that is a probable cause for error. Then accuracy of measuring sensors and their related scaling factor, yes, that is also a cause of error in PHIL. And then scaling factors associated with GTAO and GTI cards of RTDS. So all of these are correct. In a DC microgrid connected to AC grid, if power generated by PV and BSS is less than DC load connected at DC bus, then the power generated by the PV source and battery together, that is less than the load connected at that bus, then what will happen? That also we have discussed right here. Here, not here. Where was that? Here. Mm, this one. This is the microgrid PV and BS is there. Load is here, and if here the generation is less than the load, that means the load needs to be supplied by the AC side. Remaining load. The power need will flow from AC side to the DC side. The power flows from AC grid to the DC bus. Okay. Select the correct statements about RTDS, about real-time digital simulator. The simulation is done in phasor domain. This is electromagnetic EM to be transient based simulator. It's not RMS based simulator. So this is not correct. Time step of order of 10 to 20 milliseconds. This is also not correct. It is in the order of microseconds. It can simulate electrical nodes more than 1 lakh, and this is also not correct. It depends upon the number of racks and number of nodes which can be simulated are less here. And execution is real time. This is correct. That's why it is called real time, and it is because of its time step. A small time step is possible here, and execution is also very fast here. That's why it is called a real time digital simulator. Only one statement is correct here. This also we have discussed today. Select the correct statement. Let me repeat this once again. This is very important concept, and this was our these our these are the three phasors, and together we can represent it by a space phasor F. Let us call it as FABC. Okay, and it is rotating with some speed, angular speed omega, or frequency omega, and then we have another frame of reference. This is one frame of reference ABC, and we are creating another frame of reference which is this DQ. Okay, D and Q, and their resultant I call it as FDQ, and this is at some angle theta, and this is also let's say this is also rotating at some angle, same speed omega. Because this is also rotating at the same speed, this dq quantities becomes DC signal. On the other hand, alpha beta is a stationary frame. Change the color. This alpha beta is not rotating. This is stationary with respect to the ABC, and that's why because this is stationary, this also becomes sinusoid. But this is rotating. That's DQ is a rotating frame of reference. Therefore, it uh, provides us DC signals. That's why we are able to use PI controllers, and here we need PR controllers. DQ frame of reference is called synchronous frame of reference. So is this correct as per our discussion? What we have discussed? Yes, this is correct. This is also synchronous means same speed, right? That's why I call synchronous machines. It is rotating at the same speed. An alpha beta frame of reference is stationary frame of reference. This is also correct. PI controller is used in alpha beta frame. This is not correct. It should be PR. So first two statements are correct. This synchronous frame, actually this is called as a rotating frame of reference. We can call it as, this statement should also be correct here. Rotating frame of reference. Okay, same thing is explained here also. If you see, ABC. Inputs are ABC, and we get alpha and beta. This is the transformation matrix here. And from alpha beta to ABC, we can use this 2 by 3 of C transpose. This is C matrix. C matrix. And if we do 2 by 3 of C transpose, we get the inverse transformation. Similarly, ABC to DQ. Here we have cos and sine terms in the transformation matrix. And this is 2 by 3 of T transpose. And this is T. So ABC to alpha beta, ABC to DQ. And then DQ to ABC. The same thing is explained here. This was your, this is the actual phasor FT rotating at omega t, and this is the FD FQ, and this is also rotating at omega t. But alpha beta is, this is F, yeah, this is alpha axis, this is beta axis, this is stationary, this is not rotating. And you can, this is the reference. You can read about this in detail from this book. Demand response process. Okay, so this is a demand response process. Someone had asked this out last class, that's why I kept it here. So ISO determines the preferred demand volume and duration that is offered. And then aggregator receives the load data from ISO. The aggregator will select the consumer for their participation in the DR program depending upon their availability and the requirements set by ISO. Then accounting the number of interested consumer agree with the proposed demand response, the aggregator optimizes the total demand. And then the new load demand data is reported to the ISO and local distribution operators. The aggregator will do all these things. It will integrate with ISOs, it will integrate with the distribution operator, and it will also interact with the consumers. The aggregator will interact with so many stakeholders, and then it will help in the overall operation of the system. I think this is very important. You can have a look at this if you are not able to understand. You can refer to this book. This is called as a space phasor FT. So FT is it's a space phasor which is representation of ABC, uh, three-phase quantity using a single space phasor, and this is rotating at omega t. And if we have these are two different frame of reference. One is alpha beta, which is stationary, it is not moving, and one is DQ. This is DQ, and this is also rotating at the same speed as a space phasor. That's why the quantity along these two axes become DC with respect to the space phasor, because both are rotating at the same speed. But because alpha and beta is not alpha beta quantities, they become sinusoid because one is rotating and one is stationary. So with respect to this point is, it will be like this, right? It will go up. It will be a sinusoid. That's why alpha beta are stationary and we will produce sinusoids. Okay, do you have any doubt? Best of luck for your exams. What you can do is you can go through all the assignments which have been discussed, all the week 12 assignments, and you can go through all the materials which have been posted by the TAs on the Google Drive link. You can go through all of them and you'll be able to do well in your exam. no doubts, then we can end the session here. Thank you for joining. So total number of questions for in the exam. It depends. It varies sometimes. It's not fixed, but it is the questions will be similar to uh, similar to assignment questions. Most of them will be multiple choice. There might be some small numericals. There are very few numerical in this course. Most of the questions will be MCQ based, theoretical questions, conceptual questions. The numericals are very less for this course. So I would suggest you to go through all the assignments once again and go through the material, the summary material uploaded by the TS, and you'll be able to do good in the exams. Any other question? No? Okay, then we will close the session here. Thank you for joining.